13.8 billion years ago, we had the big battle between the two greatest powers in the universe, matter and antimatter. These two sides are truly equal and opposite. Each troop and antitroop have the same mass, same properties, but opposite charge. Protons, for example, have corresponding antiprotons, and electrons have positrons. When any of these pairs meet, they annihilate each other with a burst of energy. This process is reversible too, where a burst of energy can produce a pair of matter and antimatter troops. It was one of these huge bursts of energies that sparked the Big Bang, which produced equal numbers of matter and antimatter in pairs, and therefore should have ended with complete annihilation, leaving nothing but pure energy. But our universe isn't nothing. Everything around us is made of matter, meaning somehow matter overpowered antimatter despite the two being equal and opposite. It's as if the laws of nature were mysteriously tweaked to give matter an upper hand over antimatter. Now, this can only be true if physics finds a way to treat some charges differently from their identical counterparts, violating foundational physical symmetries. Of the four fundamental forces of our universe, gravity, electromagnetism, and the strong force all interact with positive and negative particles symmetrically. The fourth force, however, is a bit strange. The weak force is responsible for radioactive decay at the subatomic level, and gives fundamental particles the interesting ability to emit and transform into other particles. When comparing the weak force interactions of various particles with their antiparticles, scientists discovered something strange about the kaon. They found that neutral kaons decayed more frequently into certain particles than their antikaons did, in a way that favored the production of matter, which would explain why the universe has more matter than antimatter. However, because weak interactions are so rare and tiny, they alone cannot prove the actual magnitude of this asymmetry, meaning the existence of our universe is still a mystery. Whether there's a quirky property of physics we haven't proven yet, a fundamental force we haven't discovered yet, or a symmetry we haven't broken yet, it only takes one experiment to turn this mystery into a breakthrough.